Close your eyes and relax. Tonight, we're going on a journey through time. Not through the universe itself, but through humanity's slow, beautiful awakening to the cosmos around us. From the first curious eyes turned skyward to the most distant reaches of space we can now observe. Let's begin where it all started, thousands of years ago, under ancient skies. Long before telescopes or satellites, ancient peoples looked up at the night sky and saw patterns. They noticed 5 wandering stars that moved differently from all the others. These were the planets, though they didn't know it yet. Mercury, Venus, Mars, Jupiter, and Saturn danced across the heavens in their endless loops. The ancient Babylonians were among the first astronomers, keeping detailed records of the sky for over 1,000 years. They could predict eclipses, track the movements of planets, and understand the cycles of the moon. All of this with nothing but their eyes and patient observation. The Greeks wondered if the Earth was round or flat. A philosopher named Eratosthenes, around 240 BCE, proved the Earth was spherical by measuring shadows in 2 different cities at noon. He even calculated Earth's circumference, and he was only off by about 2%. Aristotle believed the Earth sat at the center of everything, with the sun, moon, planets, and stars all revolving around us in perfect crystalline spheres. This felt right. After all, we don't feel the Earth moving beneath our feet. For nearly 2,000 years, this Earth-centered view of the universe held strong. It made sense with what people could see. The ground felt still. The heavens moved. Why would anyone think otherwise? But in 1543, a Polish astronomer named Nicholas Copernicus published a radical idea just before his death. What if, he suggested, the sun was at the center instead? What if Earth was just another planet, spinning and orbiting like the rest? Most people dismissed this idea. It seemed absurd. Dangerous. Even. If Earth wasn't the center of everything, what did that mean for humanity's place in creation? Then came Galileo Galilei. In 1609, he heard about a new Dutch invention called a telescope. He built his own, improving the design, and turned it toward the sky. What he saw changed everything. Galileo saw mountains and craters on the moon. The moon wasn't a perfect, smooth sphere as everyone believed. It had terrain like Earth. It was a world. He discovered 4 moons orbiting Jupiter. Here was proof that not everything in the heavens orbited Earth. These tiny points of light circled Jupiter in the same way our moon circles us. Galileo observed that Venus went through phases just like our moon. This could only happen if Venus orbited the sun, not Earth. Copernicus was right. He saw that the Milky Way, that cloudy band across the night sky, wasn't a cloud at all. It was made of countless individual stars, too numerous to count, too faint to see separately with the naked eye. For these discoveries, Galileo faced the Inquisition. A church forced him to recant his support for the sun-centered universe. But the truth was out. The cosmos was far stranger and more wonderful than anyone had imagined. Johannes Kepler, a German mathematician, discovered that planets don't orbit in perfect circles. They move in ellipses with the sun at one focus. The heavens weren't as geometrically perfect as the ancient Greeks believed. Kepler found that planets move faster when they're closer to the sun and slower when they're farther away. There was a mathematical harmony to it all, a cosmic rhythm that could be calculated and predicted. In 1687, Isaac Newton published his laws of motion and universal gravitation. Suddenly, the same force that made an apple fall from a tree explained why planets orbited the sun. Gravity was universal. Newton showed that the universe operated like clockwork, following mathematical laws that applied everywhere, from Earth to the most distant star. The cosmos was comprehensible. Astronomers began measuring the distances to stars using parallax, the apparent shift in a star's position as Earth orbits the sun. In 1838, Friedrich Bessel measured the distance to the star 61 Cygni. It was 11 light-years away. A light-year is the distance light travels in 1 year, roughly 6 trillion miles. The nearest stars were trillions and trillions of miles away. The universe was unimaginably vast. William Herschel discovered Uranus in 1781, the first planet found since ancient times. The solar system was bigger than anyone knew. Later, Neptune would be discovered in 1846, predicted by mathematics before it was ever seen. Astronomers noticed fuzzy patches in the night sky called nebulae. Some thought they were clouds of gas in our own stellar neighborhood. Others wondered if they might be entirely separate systems of stars, island universes far beyond our own. In the early 1900s, a woman named Henrietta Swan Leavitt discovered something crucial. Certain stars, called Cepheid variables, pulsed with a rhythm related to their brightness. By measuring their pulse rate, you could calculate how far away they were. Edwin Hubble used Leavitt's discovery to measure the distance to the Andromeda Nebula in 1924. It wasn't a nebula at all. It was a galaxy, a vast collection of hundreds of billions of stars sitting 2.5 million light-years away. Our Milky Way wasn't the universe. It was just one galaxy among countless others, each containing billions of stars. The universe had suddenly become unfathomably larger. Hubble made another discovery that was even more shocking. He found that distant galaxies were moving away from us, and the farther away they were, the faster they were receding. This could only mean one thing. The universe itself was expanding. Space was stretching, carrying galaxies apart like dots on an inflating balloon. If the universe was expanding now, then in the past, it must have been smaller. Wind the clock back far enough, and everything in the universe must have been compressed into an infinitely small, infinitely dense point. This was the birth of the Big Bang Theory. The universe had a beginning. It wasn't eternal and unchanging. It was born, and it was still growing. In 1964, two scientists named Arno Penzias and Robert Wilson detected a faint microwave signal coming from every direction in space. This was the cosmic microwave background, the afterglow of the Big Bang itself, now cooled to just 2.7 degrees above absolute zero. This discovery confirmed it. The universe began roughly 13.8 billion years ago in an explosion of unimaginable energy and has been expanding ever since. In those first moments after the Big Bang, the universe was unimaginably hot, 1 trillion degrees or more. It was pure energy, too hot for even atoms to form. Within the first second, the fundamental forces we know today, gravity, electromagnetism, and the nuclear forces, separated from each other. The laws of physics as we know them came into being. After about 3 minutes, the universe had cooled enough for protons and neutrons to stick together, forming the first atomic nuclei, mostly hydrogen, some helium, and trace amounts of lithium. These were the only elements in the entire universe. For the next 380,000 years, the universe was opaque, filled with a hot plasma of electrons and nuclei. Light couldn't travel through it. The universe was in its dark age. Then the universe cooled enough for electrons to combine with nuclei, forming the first complete atoms. Suddenly, light could travel freely. This is the light we now see as the cosmic microwave background. For millions of years after that, the universe was truly dark. There were no stars yet, just vast clouds of hydrogen and helium, slowly swirling under the influence of gravity. Gravity pulled these clouds together, making them denser and hotter. Eventually, about 100 million years after the Big Bang, the first stars ignited. The universe lit up for the first time. These first stars were massive, hundreds of times the mass of our sun. They burned bright and fast, living only a few million years before exploding as supernova. In those supernova explosions, something magical happened. The intense heat and pressure forged new elements: carbon, oxygen, iron, gold, and all the other heavy elements that would one day make up planets and people. The explosions scattered these elements across space, where they mixed with the hydrogen and helium to form new stars, new planets. Each generation of stars enriched the universe with more complex chemistry. About 9 billion years after the Big Bang, in one quiet corner of one ordinary galaxy, a cloud of gas and dust began to collapse under its own gravity. This would become our solar system. The center of this cloud grew hot and dense, eventually igniting nuclear fusion. Our sun was born, a medium-sized yellow star, nothing special among the hundreds of billions in the Milky Way. The leftover material from the sun's formation formed a disk around it. Over millions of years, dust grains stuck together, forming pebbles, then boulders, then planetesimals, and finally planets. The inner planets, Mercury, Venus, Earth, and Mars, formed close to the sun where it was too hot for ice to exist. They're rocky worlds made of metal and stone. The outer planets, Jupiter, Saturn, Uranus, and Neptune, formed farther out where ice could exist. They grew massive by capturing huge amounts of hydrogen and helium gas. Earth formed about 4.5 billion years ago. At first, it was a molten ball of rock, constantly bombarded by asteroids and comets. It was completely inhospitable to life. A Mars-sized object called Theia collided with the early Earth. The impact was so violent that debris was thrown into orbit. This debris eventually coalesced to form our moon. The moon's presence stabilized Earth's rotation, giving us consistent seasons. This stability may have been crucial for life to develop. We owe our existence, in part, to that ancient collision. Over hundreds of millions of years, Earth cooled. Water vapor in the atmosphere condensed, raining down for perhaps millions of years, forming the first oceans. Somewhere in those ancient oceans, about 3.8 billion years ago, chemistry became biology. Simple molecules organized themselves into something that could replicate, evolve, and adapt. Life began. For billions of years, life remained simple, just single-celled organisms, bacteria and archaea, floating in the seas. But these tiny creatures were slowly changing the planet. Some bacteria evolved the ability to photosynthesize, using sunlight to convert carbon dioxide into oxygen. For the first time, oxygen began accumulating in Earth's atmosphere. This was actually catastrophic for most early life, since oxygen was toxic to them. The Great Oxygenation Event, about 2.4 billion years ago, was one of Earth's first mass extinctions. But some organisms adapted. They learned to use oxygen for energy, a far more efficient process than anything that came before. This paved the way for complex life. About 600 million years ago, multicellular life exploded in diversity. The Cambrian explosion brought the first animals with hard shells, the first eyes, the first predators and prey. Life colonized the land about 450 million years ago. Plants came first, then insects, then amphibians, and eventually reptiles. Earth transformed from a barren rock to a green world. 66 million years ago, an asteroid about 6 miles wide struck the Yucatan Peninsula. The impact released energy equivalent to billions of nuclear bombs. The dinosaurs, which had ruled Earth for 165 million years, went extinct. In the aftermath, small furry creatures that had lived in the shadows of dinosaurs had their chance. Mammals diversified and evolved. Our ancestors were among them. Humans evolved only in the last few million years. Modern humans, Homo sapiens, emerged about 300,000 years ago in Africa. In cosmic terms, we appeared just seconds ago. And yet, in that brief moment, we've done something remarkable. We've looked up at the stars and asked questions. We figured out where we came from, what the universe is made of, and how it all began. Our sun is just one of an estimated 200 to 400 billion stars in the Milky Way galaxy, each one a nuclear furnace, fusing hydrogen into helium, releasing the energy that makes them shine. The Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped structure with spiral arms extending outward. We live in one of those arms, the Orion Arm, about 26,000 light-years from the galactic center. If you could see the Milky Way from outside, it would look like a giant cosmic pinwheel, about 100,000 light-years across and 1,000 light-years thick, slowly rotating through space. At the very center of our galaxy sits a supermassive black hole called Sagittarius A star. It has a mass of about 4 million suns, all compressed into a region smaller than Mercury's orbit. Nearly every large galaxy has a supermassive black hole at its center. These cosmic monsters can have masses billions of times that of our sun, warping space and time around them. There are an estimated 2 trillion galaxies in the observable universe. Spiral galaxies like ours, elliptical galaxies that look like cosmic footballs, and irregular galaxies with no particular shape. Galaxies aren't evenly distributed. They cluster together in groups and superclusters, forming vast cosmic webs separated by enormous voids where almost no galaxies exist. Our Milky Way is part of the Local Group, a collection of about 50 galaxies. Our nearest large neighbor is Andromeda, which is actually moving toward us. In about 4.5 billion years, the Milky Way and Andromeda will collide. Don't worry, galaxies are mostly empty space, so stars rarely collide. The 2 galaxies will merge into one larger elliptical galaxy. Scientists have given this future galaxy a name, Milkomeda. Our sun will still be shining then, though Earth will likely be uninhabitable due to the sun's increasing brightness. Stars come in many sizes and colors. The smallest red dwarfs are only about 8% the mass of our sun and can burn for trillions of years. The largest stars are hundreds of times more massive and burn out in just a few million years. A teaspoon of neutron star material would weigh about 6 billion tons on Earth. These are the collapsed cores of dead, massive stars, so dense that protons and electrons are crushed together into neutrons. When the most massive stars die, they don't just become neutron stars. They collapse entirely into black holes, regions of space where gravity is so strong that nothing, not even light, can escape. Black holes aren't cosmic vacuum cleaners. If the sun magically became a black hole right now, Earth would continue orbiting exactly as it does now. The gravity would be the same, just compressed into a smaller space. Around a black hole, space and time become so warped that strange things happen. Time flows slower the closer you get to one. At the event horizon, time essentially stops. From an outside observer's perspective, we've now detected gravitational waves, ripples in space-time caused by violent cosmic events like colliding black holes. Einstein predicted these waves over a century ago, but we only confirmed them in 2015. In 2019, scientists captured the first image of a black hole's event horizon. It's in the galaxy M87, about 55 million light-years away, and has a mass 6.5 billion times that of our sun. Almost everything we can see in the universe, stars, planets, gas, dust, is made of what scientists call ordinary matter. But this ordinary matter only makes up about 5% of the universe. About 27% of the universe is dark matter, something that has gravity but doesn't interact with light. We know it exists because we can see its gravitational effects on galaxies, but we don't know what it is. Dark matter is invisible, but without it, galaxies couldn't hold themselves together. The visible matter alone doesn't have enough gravity. We're surrounded by a mysterious substance we can't see or touch. Even stranger, about 68% of the universe is dark energy, a mysterious force causing the expansion of the universe to accelerate. The universe isn't just expanding, it's expanding faster and faster. This means that in the far future, distant galaxies will move away from us so fast that their light will never reach us. The universe will seem darker and emptier from Earth's perspective. There are more stars in the universe than grains of sand on all the beaches on Earth. We estimate about 200 billion trillion stars exist in the observable universe. The universe is about 13.8 billion years old, but the observable universe, the part we can see, is about 93 billion light-years across. This is because space itself has been expanding while light travels. Beyond the observable universe, there's likely more universe we can never see. The light from those regions will never reach us because space is expanding too fast. We're isolated on our cosmic island. Planets are everywhere. We've discovered thousands of exoplanets orbiting other stars. Some are gas giants like Jupiter, others are rocky like Earth, and some orbit in the habitable zone where liquid water could exist. The closest exoplanet to us is Proxima Centauri b, just 4.2 light-years away. It orbits in the habitable zone of its star. Could there be life there? We don't know yet. With our current technology, it would take about 75,000 years to travel to Proxima Centauri. The distances between stars are so vast that interstellar travel remains beyond our reach. But we have sent messages to the stars. In 1977, the Voyager spacecraft were launched carrying golden records with sounds and images from Earth, just in case anyone out there finds them. Voyager 1 is now in interstellar space, over 14 billion miles from Earth. It's the most distant human-made object, a tiny ambassador carrying our story into the cosmos. We've been listening for signals from extraterrestrial civilizations for decades through SETI, the search for extraterrestrial intelligence. So far, we've heard nothing but cosmic silence. Given the billions of stars in our galaxy alone, many with planets, the question, "Are we alone?" feels increasingly profound. Statistically, it seems unlikely we're the only life in the universe. Yet the universe is vast, and the timescales are enormous. Two civilizations could exist in the same galaxy, but be separated by millions of years in time, or thousands of light years in space, never knowing the other existed. Our sun will continue shining for another 5 billion years or so. Then it will swell into a red giant, engulfing Mercury and Venus, and possibly Earth. Eventually, it will shed its outer layers, leaving behind a white dwarf. That white dwarf will slowly cool over trillions of years, eventually becoming a black dwarf, a cold, dark cinder. But the universe isn't old enough yet for any black dwarfs to exist. In the far, far future, trillions upon trillions of years from now, all the stars will burn out. The universe will enter an era of darkness, with only black holes and cooling stellar remnants remaining. Eventually, even black holes will evaporate through a process called Hawking radiation. After an incomprehensibly long time, 10 to the power of 100 years or more, even the largest black holes will vanish. The universe will be cold, dark, and nearly empty. This is called heat death, a state of maximum entropy where nothing changes anymore. The story of the universe, with all its light and energy, will come to an end. But right now, in this moment, we exist in the universe's golden age. Stars are shining, galaxies are forming, and life, at least here on Earth, is thriving. We are privileged to witness the cosmos in its prime. And somehow, the universe has become aware of itself through us. We are star stuff contemplating the stars, atoms arranged in such a way that we can ponder our own origins. In understanding the universe, we understand ourselves. And in that understanding, there is a profound kind of peace. Rest now. The cosmos continues its endless dance, just as it has for billions of years, and just as it will for billions more. You are part of that dance, made of the same ancient atoms forged in the hearts of stars. Sleep well, cosmic wanderer.